For decades, engineering existed in strictly partitioned worlds. Mechanical systems operated in physical isolation, separated entirely from the global digital networks that eventually grew around them. Engineering an Internet of Things system involves deploying a specific architecture that embeds digital logic and network connectivity directly into these analog environments. The core challenge of this architecture is translation. An edge device must continuously convert raw physical states into readable digital telemetry, while simultaneously taking cloud-based logic and converting it back into physical movement. Successfully managing this data loop forces a shift in perspective. To build a functional edge node, engineers must bridge the gap between physical hardware and the software that interacts with it. To build an IoT ecosystem from the ground up, we have to look at the system through first principles. Moving data from a localized physical environment to a global server and back requires a rigid 4-layer architectural stack. This block diagram outlines the complete architecture. At the bottom is the empty physical layer, followed by the local compute layer, the network transport layer, and finally the global cloud layer at the top. An engineer must understand exactly how data passes through each of these interfaces. A failure at any single layer breaks the entire autonomous network. We begin at layer 1, the physical edge. For any object to join a network, it must possess integrated electrical or electronic support. A purely mechanical object cannot interface with a digital system. This electronic foundation allows us to integrate sensors. These are the critical input mechanisms that constantly measure real-world conditions. This schematic demonstrates how a sensor detects a physical factor, like temperature, translating it into a continuous analog electrical signal. On the other end, an actuator, like a servo motor, receives a digital pulse and converts it into physical movement. This lowest layer serves exclusively as the sensory organs and muscles of the system. It can detect heat and move gears, but it possesses absolutely zero internal logic or decision-making capability. To introduce logic, the signal moves to layer 2, the localized computing layer. Here, a localized microcontroller acts as the node's brain, intercepting the raw data coming directly from the connected physical sensors. Its immediate task is translation. The microcontroller digitizes the incoming continuous analog waves, converting them into discrete, readable binary data. The hardware required depends on the complexity of the data. Lightweight microcontrollers, like the ESP32, run simple continuous C or C++ loops. They are highly efficient, designed specifically for low-power processing tasks. Heavy edge processing requires a more robust setup, like a Raspberry Pi. These act as complete microcomputers, requiring full operating systems to execute complex Python scripts and handle larger data loads. Without this local processing logic, raw telemetry remains trapped at the edge. The microcontroller serves as the essential gatekeeper, structuring physical data so it can survive the trip to the global network. Once structured, the data reaches layer 3. The challenge here is logistical, safely transporting processed packets out of the physical node and routing them to remote servers. This network topology graph shows data packets leaving the local node. Designing this exit path requires balancing bandwidth, range, and power. Short-range communication relies on Wi-Fi or Bluetooth, while remote sensors require long-range, low-power networks like LoRaWAN. Connecting the hardware is only the first step. The data also requires a specific application protocol to dictate how it speaks to the server, using HTTP for heavy structured web traffic or MQTT for lightweight continuous telemetry streams. This layer dictates the speed, scale, and energy cost of the entire system. Selecting an improper protocol will drain the battery, isolate the node, and collapse the stack. Finally, the transported data hits layer 4, the cloud. This begins the ingestion phase, where millions of packets from highly distributed edge nodes land simultaneously. To organize this influx, a cloud database framework, such as Firebase, acts as a massive global ledger, constantly recording the incoming telemetry state by state. From there, back-end logic services like Node-RED take over. These services continuously evaluate the global database against specific programming rules or complex AI models. This evaluation happens entirely without human input. Based on logic rules, the back-end automatically generates new commands, firing them down through the network and compute layers to trigger the edge actuators. The cloud layer provides the mechanism for transforming remote-controlled tools into autonomous, predictive systems. To see how this architecture performs in practice, consider the common problem of diagnosing a mechanical failure inside a home washing machine. In a traditional reactive system, the owner discovers the machine isn't spinning, calls a customer service hotline, and waits days for a technician to arrive. The technician then has to physically disassemble the machine, hunting blindly through the wiring to locate an isolated analog hardware fault. When we map the 4-layer IoT stack onto this appliance, the process changes. At layer 1, an internal load sensor immediately detects an anomaly in the motor's vibration. At layer 2, the local ESP32 microcontroller processes that voltage spike and generates a specific diagnostic fault code. This vertical flowchart tracks the remaining data path. The pulse leaves the processor, traveling up through layer 3 via MQTT over Wi-Fi. It lands in layer 4's Firebase database, instantly triggering a mobile alert before the machine finishes its cycle. By implementing this full architecture, a delayed manual mechanical crisis is solved proactively through software. The ultimate value of the Internet of Things lies precisely in this capability, extracting continuous, actionable data from the physical world. Designing systems capable of this level of autonomy requires engineers to abandon the traditional separation of hardware and software disciplines. A modern engineering problem cannot be solved in isolation. Success now requires strict fluency across the complete triad: the physical edge hardware, the local logic processor, and the global network.